Hi everyone, my name is Osmar Olivo and I'm a product manager here at MongoDB. Today I'd like to talk a little bit about all of the new features in our upcoming 3.0 release. So, as many of you may have heard, 3.0 is pretty much our biggest release ever. So in that we have a plethora of new features and capabilities, and while I can't possibly talk about all of them, I'd like to at least go in depth on some of the bigger topics and also discuss some of the new features in a little bit more detail. So I'll start off by talking about the new pluggable storage engine API. And then I'd also like to talk about WiredTiger, which is our very first supported pluggable storage engine, or second storage engine. And I'd also like to talk a little bit about the WiredTiger internals and some of the new features and capabilities it provides, such as document level locking, compression, and I'd also like to go in a little bit of in-depth on the upgrade procedure, installation, as well as some additional options it provides. So first, I'd like to talk about the pluggable storage engine API. New to 3.0, we've added a API that allows users to interface with the higher levels above the storage engine, such that they can write their own storage engine. So the vision here is, at some point we realized that mmap v1, while being a great storage engine and the only storage engine actually supported by MongoDB up until this point, does not necessarily address all possible use cases and workloads. It's not necessarily an ideal fit for a lot of them. Therefore, as opposed to trying to make it a one-size-fits-all, meets every use case engine with more options than anyone could possibly easily understand it or configure, we came up with the idea of allowing for multiple storage engines on the system, such that you can tune your system to run the optimal storage engine for your particular use case and workload. So the idea here is, at the storage engine level, we pretty much only cover the on-disk representation of the data, as well as the in-memory representation of the data and how it's accessed. It includes the in-memory concurrency model of reads and writes and updates. So everything above the stack should be unaffected by this. So in this picture I'm showing, I believe it's an accurate representation of what we consider to be the full MongoDB stack, or MongoDB ecosystem. So looking at the top line, we see the application layer of the stack. So there's content repositories, ad services, analytics platforms, pretty much anything you can plug into MongoDB from a client perspective. Then, one step below that on the stack, we have our actual query language, which runs on our native drivers. So regardless of what your underlying storage engine is going to be, you're still going to be using our query language, and you're still going to be using standard MongoDB drivers. Below that on the stack is our document data model. So again, regardless of what the storage engine is, you'll still be using the MongoDB query language to query the MongoDB document data model, JSON for those who are familiar with it. So overall, the MongoDB ecosystem should be fairly unchanged, and the underlying storage engine swap should be fairly transparent. From a tooling and management perspective, everything should be exactly the same. And from a security perspective, all of the feature sets are the same, the query language is the same. So the only things that will ideally change is the underlying storage engine mechanics, so the file format and the in-memory representation of data and the access patterns. So here we have mmap v1 as well as WiredTiger. You'll also notice that in the middle we have in-memory engine listed as experimental. So in the 3.0 release, we actually will be shipping an experimental in-memory storage engine. This storage engine, while not yet ready for the prime time of production level deployments, is still a very interesting feature to play with, try out, do some testing on, and we'd love feedback on it, as it is an experimental feature that we're going to be refining and improving, hopefully for a future release. Ideally, the way that this ecosystem will work is you shouldn't necessarily care about the specifics or internals of what underlying storage engine you run on the platform. It could be something developed by the community. It could be something put out by us. Ideally, it shouldn't matter from a development perspective or even a maintenance perspective, since all the tooling should work the same. The main thing here is that you should think about it from the perspective of use cases and workloads. So while certain workloads and use cases will be great for mmap v1, others will not be so great, but might be great for Wired Tiger. Other use cases may require an in-memory and only storage engine. And one can imagine a use case like that where you can mix and match storage engines. So perhaps you have an in-memory only primary, and then you have secondaries in either Wired Tiger or mmap, and therefore your primary should be able to handle much, much more load, since it doesn't have to worry about actually persisting any data, and the secondaries can handle that. So ideally, this will open up a lot of use cases going forward, and by no means is Wired Tiger or even this experimental in-memory engine going to be the only storage engines we provide. While we expect many members of the community to come out with new storage engines, MongoDB is going to continue to make sure that we address use cases that today are not good fits with our existing storage platforms. So some example possible future storage engines could be hardware optimized storage engines, such as for Fusion IO or SSD optimized. Other possible storage engines could be for analytics platforms. If you're running lots of Hadoop jobs, as opposed to having to transfer all of the MongoDB data over to HDFS and then run Hadoop jobs on it, or Spark, or Pig, Hive jobs, anything like that, what you actually could do is have a HDFS pluggable storage engine, and then if the data is natively being stored that way, you could just have a secondary on HDFS and run the jobs directly on that. So those are just some of the potential storage engines we're looking at. Others would be, a worm storage engine where you could write once but read many, optimized for different kinds of workloads that are commonly come up. Ideally, or at least our hope is that with mmap v1 and Wired Tiger, between the two, we cover a solid percentage of most common use cases, and we'll be filling in gaps along the way as we go. But I want to stress and emphasize that it's the bottom layer of the stack, so such that the query language will always be the same regardless of the storage engine, and the data model and everything should be fairly transparent. So realistically, you shouldn't focus too much on the details of the underlying engines and more on sort of what your use case is and which one's going to be the best fit. So all of that being said, I'd like to talk a little bit about the Wired Tiger integration more in depth. The Wired Tiger integration is by far the biggest feature in 3.0. This is a new storage engine with many, many new capabilities, and ideally should be a pretty simple plug and replace upgrade. It should not have any backwards compatibility, too many backwards compatibility issues. As well, it should be fairly transparent to DBAs from a maintenance perspective, as well as developers, as to whether they're running on mmap v1 or Wired Tiger. Ideally, all they see is the improved performance and added features. So before I get into the Wired Tiger details, I want to talk a little bit about the product itself. So why did we make the decision to go with Wired Tiger as our very first officially supported storage engine with this new storage engine API? Well, WiredTiger was kind of a great fit in that it addressed many of the weaknesses of mmap v1. So some of the weaknesses were mmap v1 did not store data compressed, so therefore it did not utilize disk space as efficiently as possible. Another perceived weakness would be the locking model. In mmap v0, which was basically the 2.6, 2.4, 2.2 branches, all of our previous storage engines up until this 3.0 release had database level locking up until 2.2, and then prior to that it was a global lock. The difference here is that WiredTiger is capable of more concurrent locking. So while we have made improvements to the mmap branch, mmap v1 supports collection level locking. For high write throughput use cases, WiredTiger is just simply a better fit. It also means that with this finer grained locking model, we can operate in much more parallel. This allows for full hardware utilization. So previously, where a CPU is not necessarily an issue, it was not necessarily fully utilized, now we should be able to max out powerful machines. WiredTiger's storage format also allows for online compaction, so you do not have to worry as much about fragmentation. And there's also a lot of features, many more than I can possibly name here, that are included in WiredTiger that have yet to be ported over to the MongoDB integration. However, it sort of paves the way and allows for easy exposure of these features as we improve, integrate, and test them appropriately. So this is just the tip, literally the tip of the iceberg as far as exposing the WiredTiger feature set. So some of the background on WiredTiger is the authors are former members of the Berkeley DB team, so they've done this before. They've been making databases for a long time, and they have a wealth of experience. WiredTiger, the product and the team, were acquired by MongoDB this last fall, and the standalone engine has already proven itself to be very efficient and stable as it's being used today in production in many large deployments. So I want to go in a little bit more depth on the document level concurrency model in WiredTiger. So document level concurrency, as I mentioned, in mmap, up until now, we've had database level concurrency. Essentially what this means is that if we have two operations being sent to the same being sent to the server, and those operations are taking place in the same database, then from a read perspective, we don't need to lock. We can have as many parallel readers as necessary. However, from a write perspective, if I'm editing a document in a database and someone else is trying to edit another document or even read another document, there is no guarantee that the edits I'm making can't be seen by those users, thus leading to a dirty write or potentially a dirty read. So in order to avoid conflicts, only one write operation is allowed to happen at any database at a time. So this is how this worked in all of our previous branches up until 2.6. Now in the 3.0 release, on mmap v1, we have collection level locking. This means that if we have multiple users writing out to different collections, as long as it's not the same collection, there's no conflict. However, if multiple users or multiple operations are going in to the same collection, then we must wait for each write operation in order to maintain a stable read-write no dirty reads, no dirty write model. Wired Tiger now improves on all of this such that it goes to the document level. What this means is unless another operation is attempting to read or write to the same document that I am currently writing to, then all those operations can happen in parallel. And if I try to read or write to a document that is currently being written to, then I get placed on, I basically wait in some queue-like system until that operation is done, and then I can apply my operations on that document. So writes no longer block all other writes, and writes no longer block all other reads unless they're being routed to the same document. And what this means is now that we can handle everything in a much more parallel fashion, CPU utilization is going to actually be a very large factor and directly correlate to performance. Essentially, if I can have as many operations going on as I have cores available on my system, so under heavy load, it's perfectly normal to see Wired Tiger fully utilizing all CPUs on a system. And in fact, if you feel that you want to improve your throughput, then adding to CPU, getting more performant CPUs should directly be able to scale out your performance in terms of read and write throughput. Another big feature in Wired Tiger, new to 3.0, is compression. By default, Wired Tiger has two compression options. So the snappy is the first option, and that is actually enabled by default. It's just that. It's a very snappy algorithm. It's a very relatively fast compression algorithm that gives you fairly good compression ratios with minimal impact on performance. So the idea here is that with Snappy doing compression, we don't utilize too many CPU cycles actually compressing and decompressing the data and get a fairly good benefit from it. The other option is zlib. Zlib gives extremely good compression ratios. However, because the compression algorithm is somewhat more complex, it's going to cost you additional CPU cycles to compress and decompress data. As I mentioned earlier, because of the document level locking model, CPU cycles now essentially directly correlate with performance. So this means that with zlib, if you're using additional CPU to compress and decompress the data, then your overall available CPU for performance, for throughput, goes down. So it's a bit of a trade-off in that use case. However, the better compression ratios means that not only should it reduce the overall utilization of storage, but it should also help with I/O in terms of when we need to go to disk to fetch data into memory. You should now be able to do that with much less I/O. So what this means is you have reduced storage costs, but you also should have reduced I/O costs when needing to go to disk, because the overall documents are just stored in a much smaller format. So deciding when to go with Snappy or zlib will purely be determined by your workload, your working set, as well as available memory on the system and the hardware. There's actually a third option which is not listed in the slide, and that is none. So there is the option to just turn compression off in Wired Tiger altogether. The reason to do that would be in a use case where the data you have doesn't compress very well either way. Therefore, you don't necessarily need to waste the additional CPU cycles trying to compress that data. So a good example of this would be something like a PDF. PDFs don't compress very well, so if you're storing PDF data in MongoDB, there's really no point in enabling compression because all you really do is slow down your overall performance. So now I'd like to talk a little bit about the WiredTiger internals. So, the file format is very different in WiredTiger, first and foremost. Data is stored as a conventional B tree on disk, but the massive difference from mmap, if that's your point of reference and what you're familiar with, is we insert every collection into one big file. Another big difference is that the indexes now have their own files. Another massive difference is that mmap v1 is named that because it took advantage of the mmap system call to memory map files directly into memory. WiredTiger does not use this approach, but as a result, it means that the in-memory and on-disk format are decoupled. So while data can be stored, compressed, and in a certain format on disk, in memory, we can transform it from the on-disk structure to a usable in-memory data structure. So this will allow for many innovative things going forward that will allow us to store the data in certain formats on disk and utilize the data differently in memory. So that there's a lot of room for innovation in that space. So going into a little bit more detail on the file layout. As I mentioned, each collection and index are going to be stored in their own file. The interesting thing about that is that now, because each collection and index are stored in their own file, we can actually take advantage of that and do things like putting indexes on their own volumes, such that the indexes can be on faster volumes, so something like SSDs, whereas the data can potentially be on slower volumes or less performant volumes. And this should help yield, overall performance if your working set doesn't fit in memory, because now you can access your indexes very, very quickly. Main differences as well in the file format is that because the file format is so different on WiredTiger and mmap v1, they're not interchangeable. WiredTiger will fail to start if it detects mmap v1 files in its database path, in the DB path, and vice versa. mmap v1 will fail to start if it detects WiredTiger files in its DB path. So when you make a decision to use a storage engine at a server level, the only way to switch that would be to reload or resync all of the data from another member. Another departure from a previous paradigm is that WiredTiger does not do in-place updates. It actually will rewrite the document to the end of the file every time. This means a few things. So for one, fragmentation is much less of an issue in WiredTiger as it periodically compacts the older overwritten documents. It also means that there's really no need for padding factor because growing documents are no longer as large an issue in WiredTiger as they are in mmap. What I mean by this is that if you have a document that is consistently growing, in mmap, what we would have to do is allocate some padding factor to account for growth. And if we overgrew that factor, we would have to reallocate that at the end of the file. Now, since we're always contiguously writing to the end of the file anyway, there's really no need for padding factor, so your overall database and document sizes should go down. And we get much more concurrent, contiguous I/O happening. Other interesting changes in the file layout include the fact that the concept of a database doesn't really exist as far as the file format is concerned. So while in WiredTiger all database files were associated with each other, such that every database file knew of all its underlying collections and indexes, Now, as I mentioned, every collection has its own file and every index has its own file. So the concept of a database is purely logical. It's purely a grouping and organization method, and does not at all map in any way to the file format. Other differences are that the journal has its own folder under the database path. That's not really a difference. mmap did it as well, but as I mentioned before, now you still have the option to move the journal off to its own volume, and the new option to move the indexes off to separate volumes as well. --db path does still exist. So even though WiredTiger does not have a layout concept of a database, you can still separate the files by database and have each database own its own volume. Well, so I want to talk about some of the major changes. So WiredTiger does not support some of the older built-in features to mmap. So some changes that have happened are we have deprecated the system.indexes and system.namespaces collections. Those are mmap v1 specific collections. And unfortunately, there are lots of drivers and lots of tools out there that leverage sort of this loophole to access namespace data or access index data. So in this release, we're standardizing around using the system metadata commands to access them. So instead of viewing the indexes through system.indexes, you should probably view the indexes using the getIndexes command. Same idea with namespaces. Instead of viewing the system.namespaces collection directly, you want to say get namespaces. So this has been generalized and abstracted such that this will work regardless of what underlying storage engine you're using. Unfortunately, several of our older drivers or community drivers or tools that have been built relied on these sort of underlying systems as opposed to using the getIndex or getNamespaces commands directly. So many MongoDB tools or drivers will need to be upgraded to the latest releases for each respective driver in order to properly work with 3.0 on WiredTiger. So that is definitely something to be aware of going forward, is you should be running the latest drivers on 3.0. I want to talk a little bit about how memory is managed in WiredTiger. So WiredTiger uses two caches. It uses the WiredTiger engine cache, and it uses the file system cache. mmap v1 only used the file system cache. It only used one cache. Now, this trails back to my previous statement of the memory representation and the on-disk representation are decoupled. So as a result, we can't use the raw files in the format that they're stored in. For one thing, the data is compressed. So when actually accessing documents and collections in memory, we need to have them all in their in-memory representation. So this means that the WiredTiger engine cache is what's going to actually be holding your working set, whereas the file system cache is just going to hold the cached version of the files that are being used. So ideally, you want to tune this appropriately such that your WiredTiger engine cache can hold your working set, or at least a majority of your working set, such that you rarely have to go down to your file system cache and do the mapping from the file format to the in-memory format. And from that space, you would like to avoid the file system cache needing to page to disk, because that will involve doing I/O, which can be very costly. So it's an interesting change from how memory was managed in mmap v1. Another difference is the defaults. So since mmap v1 only had one cache, you never really had to worry about knowing how much memory was allotted to the file system cache. It just used all the memory that was available to it. With WiredTiger, by default, we will choose 50% of available system memory for the WiredTiger cache and the other 50% for the file system cache, or 1 gigabyte, depending which is higher. So on a particularly small system, you might only be able to get 1 gigabyte for the WiredTiger cache, but for most systems, it should just on average be 50% of available memory. Another slight difference is the way that data is written to disk. So whereas mmap v1, we just did msync flushes of our data files, in WiredTiger we have this concept of checkpoints. So a checkpoint will basically guarantee that all of the data is consistent up to that checkpoint. By default, checkpoints are performed every 60 seconds, which was similar to our upper bound in mmap v1. The main difference is that in mmap v1, the operating system had the option to flush before the 60-second upper bound was hit, dependent on workload. With WiredTiger, checkpoints will by default be performed every 60 seconds or after 2 gigabytes of data are written. The operating system will not implicitly trigger checkpoints, as it does with mmap v1. Another situation where I/O could occur is when the WiredTiger cache is full. In that case, pages must be evicted such that we can page in the data that is being requested into memory. That is not the same thing as a checkpoint, however. So a checkpoint will have to ensure that the entire database is in a consistent state. Another aspect of going to disk is journaling. So the WiredTiger journal functions a little bit different than the mmap v1 journal. For one thing, we can no longer set journal commit intervals. WiredTiger journal actually adds operations and changes in as they occur. It no longer commits them in batches as mmap v1 does. So this means that there is no commit interval. Things will be journaled as they come in. Aside from that, journaling semantics from a developer perspective should be very similar. J-true write concern should work just the same as it always has. You can disable the journal if necessary. And after each checkpoint, after each data file flush equivalent, the old journal files get truncated such that we know that we had a consistent flush. So in case of a failure, when we return, if the journal files are present with data in them, we know that we had an unclean shutdown and we need to replay the journal to get all of the data that came in since the last checkpoint, similar to how mmap v1 works. One big difference is that the data files are always consistent. So what this means is that even if you have an unclean shutdown, in mmap v1, running with journaling was necessary in order to confirm that you do not have corrupt data files. So it would either clean up the corruption or detect corruption in the event of an unclean shutdown. With WiredTiger, the way that the data files are written and synced up, you actually have a guarantee that the data files are always consistent, even with an unclean shutdown. So as a result, running with no journaling becomes slightly safer. If you do not have the journal running and you have an unclean shutdown, you'll lose all the data since the last checkpoint. However, you do not run the risk of your data being corrupt as you do with mmap v1. So in terms of a durability, data recoverability model, potential tuning options are more broad in WiredTiger in that you could disable the journal to get better throughput and potentially use replication as a durability model. Whereas with WiredTiger, that was less of a viable option as it could potentially corrupt your database. As with mmap, that was less of a viable option as it could potentially corrupt your database. Other major changes are, as of the 3.0 release, we no longer support 32-bit versions of the server. We still produce 32-bit versions of the server, but only for testing and development purposes. From a support perspective, no one should be running MongoDB 3.0 on 32-bit systems. And WiredTiger, in fact, does not work on 32-bit systems. Another change is that MongoDB 3.0 is not supported on Solaris, whereas previous versions have been. There's work being done, and we're looking into the viability of porting it to Solaris such that it can be supported, but at this time, as of for release, we do not intend to be able to support Solaris. Aside from that, all of our standard supported platforms are the same: Linux, Windows, Mac OS X. And generally speaking, the features and performance enhancements should be fully supported, and document level locking should help you see improvements in all of these platforms. So now I just want to talk a little bit about how do I actually run the thing, what are the major changes operationally speaking. As I mentioned before, all of our tooling should work exactly the same regardless of whether you're running WiredTiger or mmap or any other storage engine. So the main difference in your day-to-day process of launching a server is this -- storage engine flag. So today, since WiredTiger is the only officially supported storage engine, you would just say -- storage engine equals WiredTiger as part of your startup parameters or config file. That'll start up a server running WiredTiger. As with our experimental in-memory system, it's the same flag would be used, just with a different value. And with any other potential storage engine that is written against our API, all you would do is just tie it in and hardwire it into this flag with the appropriate name passed in. So operationally speaking, launching a new system on WiredTiger should be as simple as adding this flag to your config file. Now, if you already have a running system and you want to upgrade to WiredTiger, it's a little bit different. So as I mentioned, the data file formats are incompatible. And ideally, you don't want to start from scratch and have to, start from scratch all over again. So since the data files are incompatible, there's two options here. One is you add a replica set member or start up a new system, and then you Mongo dump, Mongo restore, just load all of the data back in. Another option is adding a new member to a replica set that happens to be running on WiredTiger and allowing it to do a full initial sync of the data. This way you can actually upgrade without any interruption to your system, and it'll happen as a background process, and then when all of the data is fully synced up, all you would have to do is swap out the WiredTiger node as a new primary, and then do a regular rolling upgrade as you usually would. So the big key factor of this is that we support running replicas with mixed storage engines. So it's perfectly viable to have a mmap v1 primary with a WiredTiger secondary, and vice versa. Now, the main thing to watch out for here are going to be the differences in throughput. It's entirely possible to get such good throughput on one engine such that the other engine can't necessarily keep up. And as a result, since they have different performance characteristics, you want to make sure that you have allocated appropriate oplog sizes and things like that to be able to stably run in mixed versions under high load. Another big difference is that you cannot just copy the raw data files, because as I mentioned, the data file formats are fundamentally different and incompatible. If WiredTiger realizes that there is an mmap data files in its DB path, it'll fail to start, and vice versa. a developer and admin perspective, what does this mean for options or custom configurations I've been running on so far? What's changed? So for the most part, most of the previous options should still work. Journal, no journal, upgrade, repair, all of these still apply. Some options, however, are either no longer relevant or only relevant to mmap v1. So these options are things that may no longer necessarily make as much sense. So things like -- small files. Now we actually write everything off to one file. Sync delay has been replaced with a WiredTiger equivalent. No pre-alloc. WiredTiger handles that doesn't necessarily need to do pre-allocation because it's writing to one file. As I mentioned, commit intervals and quotas. It's actually a typo here. Directory per DB does work on WiredTiger as well as mmap. So sorry for confusion if that shouldn't be there. So one other topic in terms of options is our tools in MongoDB 3.0 have been revamped somewhat in order to ensure that they work on both WiredTiger as well as mmap v1. The main difference here is the --db path flag for the Mongo restore, Mongo dump, Mongo import, Mongo export that has been deprecated. The reason for this is the --db path allowed you to talk to the data files directly without requiring a running MongoD. However, since the data file formats are going to be different as we scale out more storage engines, the key problem here is going to be keeping this up to date and ensuring it works with all storage engines. So in order to allow our tools to work with community storage engines as well as future storage engines, we've deprecated this flag and require that you have a running MongoD in order to be able to dump and load data. We've also made adjustments to our dump and load tools such that the performance difference that used to be seen when running on the raw data files versus running on a MongoD should be lessened. The tools should be much, much more performant and concurrent in 3.0 than they have been in the past. So this concludes the presentation. This has been an in-depth look on the new 3.0 release as well as sort of what's coming up in the WiredTiger system, what the internal details are. And we'll do a few minutes of Q&A. So we have about 10 minutes. So I see that some questions have been flagged. I'll start going through those. So the first question is write performance and use of JS client with 3.0. So the write performance and use of the JavaScript client. So I'm assuming you're talking about Node.js here. So depending on how you structured your application, the Node.js driver in particular is interesting in that it is one of our only single-threaded drivers. I believe it's only matched with PHP. So this means that overall performance shouldn't necessarily go up in terms of speed, but in terms of throughput and concurrency, it will. So ideally what you would do is be able to launch multiple threads, or in the case of Node.js or PHP, multiple processes in order to be able to more concurrently speak with the system. Something else that has actually been a large improvement in this space from the 2.6 release was the use of batch operations, so batch writes and batch updates. This allows you to get more throughput on the system on just one connection, as opposed to having to open up lots of concurrent connections. So this is still true on WiredTiger. We highly recommend using batch operations per connection per thread, as opposed to each operation utilizing one connection. The next question is, can you talk about WiredTiger and use cases where reads and writes are equally important? Does WiredTiger improve reads? So, strictly speaking, no. WiredTiger does not directly improve reads. So in read-only workloads, one can imagine that WiredTiger and mmap would have comparable performance, or the gulf in performance wouldn't be so very large, because there's very little locking going on when you're only doing reads. However, if you're doing reads on a system that is taking a reasonable number of writes, then that means that those reads can be blocked on those writes in mmap v1. So in a use case like that, where you have a mixed workload, you should see improvements in WiredTiger, because reads will no longer wait on writes that aren't hitting the same document. So I'd say a question, have you made performance comparisons, including graphs, between Snappy and zlib compression, CPU, storage, RAM utilization under the same load? So the answer is yes. We have tested both Snappy, zlib, and none as well to see what the overall performance comparison is going to be, what the CPU hit, and what the storage hit is. Personally speaking, however, I'd say that it's going to vary. It's going to depend highly on workloads. So depending on what kind of data is being sent, if it's highly compressible data, then Snappy and zlib may perform relatively the same. If it's data that compresses really well on zlib but less so on Snappy, then you're going to see different comparisons. If you're running on PDF files, then the overhead, to the actual benefit of storage will be minimal. So I'd say realistically this is going to have to depend on a case-by-case basis. There will likely be graphs and information that are released that sort of give guidelines on what to be expected, what kind of compression ratios, what kind of performance hit overall. But generally this is going to vary from case to case. So I would look at it from a use case perspective and only use any information we provide externally as rough guidelines. What is the cost of decoupling disk compressed files to memory formatted files in terms of RAM and CPU? So, the cost is going to be, from a RAM perspective, is tunable, as I mentioned. So by default, the WiredTiger cache will utilize 50% of available memory. This can be tuned up or down. Generally speaking, you'll probably want to tune it up such that your working set fits in memory. However, depending on what your working set is, and sorry, the question seems to have disappeared. Depending on what your working set is and what the overall usage is, what the overall data churn is, the cost will vary. So mapping from our file system cache to our WiredTiger cache, that's going to be decompressing the data and transforming it into the in-memory B-tree structure we use. Whereas going to disk is going to be a fixed cost. So essentially what you'll have to take into account here is going to be what is your compression ratio versus what is your working set size. And if your working set size can fit in your WiredTiger cache, then you'd want to tune that cache up to make sure that all of your working set fits in memory. So another question is, checkpoint can be forced more frequently than 60 seconds with WiredTiger. By default seems to imply yes. So checkpoints can be forced more frequently than 60 seconds. So by default, the value is set to 60 seconds, or 2 gigabytes of data being written. But you can tune checkpoints to happen more frequently or less frequently, depending on what you're trying to achieve from a durability or performance perspective. Question is, does WiredTiger need to decompress the whole page, or does decompression happen at a doc level? So decompression happens at a page level. So we do decompress pages, not individual documents. So the question here is, can compression be disabled at a per collection basis? The answer to that is currently no. This would be a natural next step, is enabling it such that compression can be disabled or different compression algorithms can be used per different collections. One can also imagine being able to even have different storage engines per database or per collection. But that's something to be done for a future release. As of the 3.0 release, the compression, the block compressor set is going to be at a node level. The question here is, with the option to choose different storage types for each replica, would it be a concern that a replica would gradually lag behind due to difference in write performance? Yes. So I believe I mentioned that is certain replicas may not be able to keep up with the workload, and as a result, what we'll need to do is either allocate an appropriate oplog or throttle the writes in such a way that certain replicas can keep up with the kind of workload. The question here, will there be encryption? Sorry. So what about encryption features? Do we still need to use OS disk level encryption feature to have encryption of the data at rest? So encryption is an interesting topic. So one can imagine that now with the ability to compress data, it should be a fairly simple or at least not too difficult task to add in an encryption library in its place. And that's true. So the things about encryption is that it's not so much about the actual encryption, it's about the key management. So as a result, in 3.0, encryption is not going to be supported because it's currently not supported in WiredTiger. But it's something that we're definitely looking into in terms of deciding how key management would be handled, as well as what actual encryption algorithms can be offered. So for 3.0, the recommended approach would be to use a file system level encryption protocol, such that you encrypt all of the files on the file system, not just the database files. So I'll answer one or two more questions as we're short on time. So this question is, am I correct in assuming that the new concurrent writes ability in 3.0 will make it even faster to use SSDs over hard disk drives? Or would the difference between SSDs and spinning disks only be noticeable in heavy write situations? So this is a very interesting question, and it's going to depend. So concurrent writes means that in-memory concurrency is handled concurrently. However, or is handled in more parallel way. However, the checkpoints is really when we're going to be writing data to disk. And so in that aspect, we should have comparable performance on SSDs as we have had in the past. And from a hard disk perspective, or spinning disk perspective, since the writes are going to be a little bit more contiguous, you may see better performance writing contiguously as opposed to the random I/O. So this is a benefit of no longer doing in-place updates. Under high update workloads, for example, we're going to do a lot less random I/O than we did on mmap v1. However, there always has been sort of a gulf in the difference between SSDs and spinning disks is going to be good on any database. So I wouldn't say that the difference is even faster than it has been in the past, but there is a very noticeable difference between SSDs and spinning drives. drives. There's also a working set question, so depending how often you try to access things that aren't in memory, then an SSD may be beneficial as opposed to paying the full price of a spinning disk page fault in seeking and retrieving that data. An SSD is much, much better at random access. Okay, so this will be the last question I answer. It's actually a very interesting one. How does performance of WiredTiger compare to mmap when there is only one writer, no readers, and rapid document insertion? So this is the single-threaded problem that I described answering the JavaScript question. So mmap single-threaded is essentially not going to bottleneck on the lock. It's going to bottleneck on the fact that you're doing one operation at a time. WiredTiger, same case. From a single operation perspective, it doesn't matter how concurrent the locking model is. It's just going to handle one thing at a time because that's how it's being written. So because the locking model is more complex on WiredTiger to mmap, and there's also just a lot more going on under the hood, I would imagine that mmap will likely be more performant in a single-threaded case than WiredTiger. So WiredTiger isn't necessarily faster from the point of view of individual operations are faster. It's much more concurrent so that you can get a lot more operations done in the same amount of time. So from that perspective, there is a key difference in operation speed versus concurrency. Okay, so I'll be wrapping up now in terms of questions. Please stay on the line as we have a brief survey for you all to fill out. Thank you.